Have you ever tried to count grains of sand on a beach? It's impossible, right? Well, chemists face a similar problem when they work with atoms and molecules. These tiny particles are incredibly small and numerous. So, how do we count them? We use a special unit called the mole. Think of a mole like a dozen. A dozen means 12 of something. A mole means a specific, very large number of particles. This concept is super important in chemistry. It helps us connect the microscopic world of atoms with amounts we can actually measure in the lab. Isn't science neat? Now what is this magic number? It's called Avogadro's number. Named after the scientist Amedeo Avogadro, this number is approximately 6.022 times 10 to the power of 23. That's 602 sextillion, 200 quintillion. Whoa, that's a huge number. So 1 mole of anything, atoms, molecules, ions, even basketballs if you could gather that many, contains Avogadro's number of those items. Imagine having a mole of donuts. That would be a lot of donuts, probably more than exist on Earth. This number provides a consistent way for scientists everywhere to talk about the same amount of a substance at the atomic level, which is incredibly useful. So, we know a mole is a count, but how does this relate to something we can weigh? That's where molar mass comes in. The molar mass of a substance is the mass, usually in grams, of 1 mole of that substance. You can find the atomic masses of elements on the periodic table. For example, carbon has an atomic mass of about 12 atomic mass units. This means that 1 mole of carbon atoms has a mass of about 12 grams. For a compound like water, you add up the atomic masses of all the atoms in 1 molecule, 2 hydrogens, and 1 oxygen. This sum then becomes the molar mass in grams per mole. Using the mole concept in molar mass, chemists can easily convert between the mass of a substance and the number of particles in it. If you know the mass of a sample, you can figure out how many moles it contains. And if you know how many moles you have, you can calculate the mass. This is fundamental for chemical reactions because reactions happen between specific numbers of atoms and molecules. The mole lets us scale up those tiny interactions to quantities we can see and handle. It's like a recipe for chemicals. You need the right amounts for things to work. Gases are all around us. The air we breathe is a mix of gases. But what makes gases so different from solids or liquids? Well, for starters, gases don't have a definite shape or volume. Think about it. If you have a balloon, the air inside takes the shape of the balloon. If you let that air out into a room, it spreads out to fill the entire room. It doesn't just sit in a puddle on the floor like water would. This happens because gas particles are far apart and move around randomly, not strongly attracted to each other. They are free spirits. Another super cool property of gases is their compressibility. You can squeeze a gas into a smaller space. Imagine a bicycle pump. When you push down on the handle, you are compressing the air inside the pump, forcing it into your tire. This is possible because there's a lot of empty space between gas particles. Solids and liquids, on the other hand, are much harder to compress because their particles are already packed closely together. This compressibility is why we can store large amounts of gas, like natural gas for our homes, in tanks under pressure. Pretty handy, right? Gases also love to spread out, a property called diffusion. If someone opens a bottle of perfume in one corner of a room, eventually, you'll smell it in the other corner. Those perfume particles, which are in a gaseous state, move and mix with the air particles until they are spread evenly throughout the room. The same thing happens if you bake cookies. The delicious smell diffuses through your house. Gas particles are constantly in motion, bumping into each other and spreading out. This natural tendency to mix is a key characteristic of all gases and happens without any stirring. So to sum it up, gases fill any container they're in, they can be squished, and they spread out all by themselves. These properties, lack of definite shape or volume, compressibility, and diffusion, are all because gas particles are tiny, far apart, and always moving randomly at high speeds. Understanding these basic behaviors is the first step to understanding the more complex laws that govern gases. It's like getting to know the players before you can understand the game. It's all about those zippy little particles and the space between them. Let's dive into some famous gas laws. First up is Boyle's Law, discovered by Robert Boyle. This law talks about the relationship between the pressure and volume of a gas, as long as the temperature and the amount of gas stay the same. Boyle found that if you increase the pressure on a gas, its volume decreases proportionally, and if you decrease the pressure, its volume increases. Think of squeezing a soft sealed water bottle with some air in it. As you squeeze harder, increase pressure, the air inside takes up less space, volume decreases. Mathematically, we say pressure is inversely proportional to volume. Next we have Charles's law from Jacques Charles, a scientist who was also a keen balloonist. Charles's law describes how the volume of a gas changes with temperature, provided the pressure and amount of gas are kept constant. He discovered that if you heat a gas, its volume increases. If you cool a gas, its volume decreases. This is why a hot air balloon rises. The heated air inside expands, becomes less dense than the cooler air outside, and floats up. So volume is directly proportional to its absolute temperature. Remember to use Kelvin for temperature here, science friends. Then there's Gay-Lussac's law, named after Joseph Louis Gay-Lussac. This law connects the pressure of a gas to its temperature, when the volume and amount of gas don't change. Gay-Lussac found that if you increase the temperature of a gas in a fixed container, its pressure increases. If you cool it down, the pressure decreases. Imagine a sealed can of an aerosol spray. If you heat it, the pressure inside builds up, which can be dangerous. That's why there are warnings on those cans not to incinerate them. So, pressure is directly proportional to absolute temperature. Again, absolute temperature in Kelvin is key. These three laws, Boyle's, Charles's, and Gay-Lussac's, are foundational for understanding how gases behave under different conditions. They show us that pressure, volume, and temperature are all interconnected. Change one, and at least one of the others is likely to change too, in a predictable way. These aren't just abstract rules, they explain everyday things, from how our lungs work to why tires might look a bit flat on a cold morning. Science is all about these connections. Remember Amedeo Avogadro from our discussion on moles? Well, he didn't just give us a giant number, he also came up with a very important law about gases. Avogadro's law states that equal volumes of all gases, at the same temperature and pressure, contain the same number of molecules, or moles. Think about that. It doesn't matter if the gas is helium, oxygen, or carbon dioxide. If you have a 1-liter bottle of helium and a 1-liter bottle of oxygen, and they're both at the same cozy room temperature and atmospheric pressure, they have the same number of gas particles inside. Wow! This means that the volume of a gas is directly proportional to the number of moles of the gas, as long as the temperature and pressure are kept constant. So, if you double the number of gas molecules in a container like blowing more air into a balloon, the volume will double, assuming the balloon can stretch, and the outside pressure and temperature don't change. If you have the amount of gas, the volume will have. It's a straightforward relationship. More gas stuff means more space taken up. This makes intuitive sense, doesn't it? Avogadro's law leads to another useful concept, molar volume. The molar volume of a gas is the volume occupied by 1 mole of that gas. Scientists often use a standard reference point called standard temperature and pressure, or STP. STP is defined as 0 degrees Celsius, which is 273.15 Kelvin and 1 atmosphere of pressure. At STP, 1 mole of any ideal gas occupies a volume of approximately 22.4 liters. That's a pretty handy number to remember. So, whether it's 1 mole of lightweight hydrogen gas or 1 mole of much heavier sulfur hexafluoride gas, at STP, they both take up 22.4 liters. This idea is incredibly useful for chemists. If they know the volume of a gas at STP, they can quickly figure out how many moles of that gas they have, and vice versa. This simplifies calculations in stoichiometry, especially for reactions involving gases. For example, if a chemical reaction is expected to produce 44.8 liters of a gas at STP, a chemist knows that means 2 moles of that gas will be formed. Avogadro's insights really helped connect the macroscopic properties of gases like volume to the microscopic world of atoms and molecules. Science is about building those bridges. Section 5, the ideal gas equation, putting it all together. So we've learned about Boyle's law, which deals with pressure and volume, Charles's law, focusing on volume and temperature, Gay-Lussac's law, which is about pressure and temperature, and Avogadro's law concerning volume and moles. That's a lot of laws. Wouldn't it be great if we could combine them all into one super equation? Well, good news, science fans, we can. It's called the ideal gas equation, and it looks like this: PV equals nRT. This powerful equation relates all 4 important variables for a gas: pressure, P, volume, V, the number of moles, N, and temperature, T. It's a cornerstone of chemistry and physics. Let's break down the equation. P is for pressure, usually measured in atmospheres, ATM, pascals, Pa, or millimeters of mercury, mmHg. V is for volume, typically in liters, L. As we know, N represents the number of moles of the gas. T T stands for the absolute temperature and it be in Kelvin, K, for this equation to work correctly. And then there's RR is called the ideal gas constant or sometimes the universal gas constant. It's a special number that makes the equation balance out, and its value depends on the units you use for pressure and volume. A common value is 0.0821 LATM mol K. The ideal gas equation is called ideal because it describes the behavior of an ideal gas. An ideal gas is a theoretical gas whose particles take up no volume themselves and have no attractive forces between them. Real gases, of course, have particles with tiny volumes, and they do have tiny attractions. However, at most common temperatures and pressures like not too cold and not too high pressure, most real gases behave very much like ideal gases. So this equation gives us very good approximations for what's happening in the real world. It's a fantastic tool for scientists and engineers. With PV equals nRT, if you know any three of the variables, P, V, N, or T, you can calculate the fourth one. Want to know the pressure inside a container of a known amount of gas at a certain volume and temperature? Use the equation. Need to find out how many moles of gas are in a weather balloon that has expanded to a certain volume at a high altitude where pressure and temperature are different? The ideal gas equation is your friend. It's a versatile and widely used formula that brings together so much of what we know about gases. Isn't that elegant? Section 6. Sharing is caring, Dalton's law of partial pressures. What happens when you have a mixture of gases in one container? Like the air we breathe, which is mostly nitrogen and oxygen, plus a little argon and other gases. Do they all fight for pressure dominance? Not exactly. This is where Dalton's law of partial pressures comes into play, thanks to John Dalton. This law states that in a mixture of non-reacting gases, the total pressure exerted is equal to the sum of the partial pressures of the individual gases. The partial pressure of a gas is the pressure that gas would exert if it were the gas in the container at the same volume and temperature. So imagine you have a container with gas A, gas B, and gas C. The total pressure inside that container, P_total, is simply the pressure of gas A, P_A, plus the pressure of gas B, P_B, plus the pressure of gas C, P_C. It's like each gas is doing its own thing, contributing its own bit to the total pressure, without really minding the others are there. This is because in an ideal gas mixture, the gas particles are far apart and don't interact much. Each gas particle collides with the container walls independently, contributing to the overall pressure. A common real-world example is the air around us. Atmospheric pressure is the sum of the partial pressures of nitrogen, oxygen, argon, carbon dioxide, water vapor, and other trace gases. Oxygen makes up about 21% of the air, so its partial pressure is about 0.21 atmospheres at sea level, where total pressure is about 1 atm. This partial pressure of oxygen is crucial for our breathing. Another application is when chemists collect a gas produced in a reaction over water. The collected gas will be mixed with water vapor. To find the pressure of the dry gas, they need to subtract the partial pressure of water vapor, which depends on temperature, from the total measured pressure. Dalton's law is super useful in many fields. Scuba divers need to understand partial pressures because high partial pressures of certain gases, like nitrogen at depth, can have dangerous physiological effects. In medicine, the partial pressures of oxygen and carbon dioxide in the blood are critical indicators of respiratory health. So, this law isn't just an abstract concept, it has real consequences and applications. It helps us understand and manage gas mixtures in a variety of important situations, showing how individual components contribute to the whole. Teamwork makes the dream work, even for gas molecules. Section 7, Race to Escape. Graham's law of diffusion and effusion. We talked earlier about diffusion, how gases spread out to fill their container. But do all gases diffuse at the same speed? Nope. Lighter gases spread out faster than heavier gases. This relationship was quantified by Thomas Graham, and it's known as Graham's law of diffusion. The law states that the rate of diffusion of a gas is inversely proportional to the square root of its molar mass. That sounds a bit complicated, but it just means that if a gas is made of lighter particles, those particles will move and spread out more quickly than particles of a heavier gas, assuming the temperature is the same. Now, there's a closely related term called effusion. Effusion is when gas particles escape from a container through a tiny hole, like air slowly leaking out of a pinhole in a balloon. Graham's law applies to effusion too. The rate of effusion of a gas is also inversely proportional to the square root of its molar mass. So, if you have two different gases at the same temperature in separate containers, each with an identical tiny pinhole, the gas with the smaller molar mass will effuse, leak out, faster. It's like a race and the lighter runners are quicker. Think about helium balloons. Helium is a very light gas, molar mass about 4 grams per mole. Air is mostly nitrogen, molar mass about 28 grams per mole. And oxygen, molar mass about 32 grams per mole. This is why a helium balloon deflates much faster than an air-filled balloon. The tiny helium atoms can effuse through the microscopic pores in the balloon material much more quickly than the heavier nitrogen and oxygen molecules. Another example of diffusion is the smell of ammonia, NH3 molar mass about 17 grams per mole, versus the smell of hydrogen sulfide, H2S molar mass about 34 grams per mole, the rotten egg smell. Ammonia will diffuse faster. Graham's law has some very important practical applications. For instance, it was used in the past for separating isotopes of uranium. Uranium-235, which is needed for nuclear reactors and weapons, is slightly lighter than the more common uranium-238. By converting uranium to a gaseous compound, uranium hexafluoride, and allowing it to effuse through many porous barriers, scientists could gradually enrich the U-235. This process, called gaseous diffusion, is a testament to how even subtle differences in mass can be exploited using scientific principles. So size, or rather mass, really does matter when it comes to how fast gases move. Section 8. Chemical recipes, stoichiometry and formulas. Now let's switch gears a bit and talk about chemical recipes. That's essentially what stoichiometry is. It's the part of chemistry that deals with the quantitative relationships. That means the amounts of reactants and products in chemical reactions. When chemists run a reaction, they need to know how much of each starting material, reactant, to use to get a certain amount of the desired substance, product. Stoichiometry uses the mole concept and balanced chemical equations to figure this out. It's like knowing you need 2 cups of flour and 1 cup of sugar to bake a cake. The first step in any stoichiometry problem is a balanced chemical equation. A balanced equation is like a perfectly written recipe. It shows the reactants on the left side of an arrow and the products on the right side. The key thing is that the number of atoms of each element must be the same on both sides of the equation. This follows the law of conservation of mass, which states that matter cannot be created or destroyed in a chemical reaction. Balancing equations often involves adjusting coefficients, the numbers in front of the chemical formulas, until all atoms are accounted for. Before we can do much with stoichiometry, we also need to understand chemical formulas. There are 2 main types, empirical formulas and molecular formulas. The empirical formula gives the simplest whole number ratio of atoms of each element in a compound. For example, hydrogen peroxide has an empirical formula of HO. The molecular formula, on the other hand, gives the actual number of atoms of each element in a molecule of the compound. The molecular formula for hydrogen peroxide is H2O2. Sometimes the empirical and molecular formulas are the same, like for water, H2O. Once you have a balanced equation, the coefficients tell you the mole ratios. For example, in the reaction 2H2 plus O2, 2H2O, the coefficients tell us that 2 moles of hydrogen gas react with 1 mole of oxygen gas to produce 2 moles of water. These mole ratios are the heart of stoichiometric calculations. You can use them to convert from moles of one substance to moles of another in the reaction. Then, using molar masses, you can convert those moles to grams, or vice versa. This allows chemists to predict yields, determine limiting reactants, the ingredient that runs out first, and make chemistry practical. Section 9. Why all this matters: moles and gases in our world. So we've journeyed through moles, dived into the behavior of gases, and even peeked at chemical recipes with stoichiometry. You might be thinking, wow, that's a lot of concepts, Bill. But why is all this so important? Well, these ideas are not just for passing chemistry exams, they are fundamental to understanding the world around us, and to making incredible technological advancements. The mole concept, for instance, is the chemist's bridge between the invisible world of atoms and the macroscopic world we can measure and manipulate. Without it, precise chemical manufacturing, from medicines to materials, would be impossible. The gas laws we discussed, Boyle's, Charles's, Gay-Lussac's, Avogadro's, and the ideal gas equation, are critical in countless applications. Engineers use them to design engines, from the ones in your car to powerful jet engines. Meteorologists rely on them to understand and predict weather patterns as air masses move and change temperature and pressure. Anesthesiologists use precise mixtures of gases and understand their behavior in the human body to keep patients safe during surgery. Even the simple act of inflating a tire or using an aerosol can is governed by these principles. These laws help us harness the power of gases safely and effectively. And stoichiometry, it's the backbone of chemical synthesis and industry. Whether scientists are developing new life-saving drugs, creating more efficient fertilizers to feed a growing global population, or designing novel materials for electronics and construction, they need stoichiometry. It ensures that reactions are efficient, waste is minimized, and products are pure. It's about precision and control in the chemical world. Understanding how much of what reacts to form something else is absolutely essential for any chemical process, from a small lab experiment to a massive industrial plant producing tons of material. Ultimately, the mole concept, gas laws, and stoichiometry are powerful tools that allow us to describe, predict, and control chemical and physical changes. They empower scientists and engineers to solve real-world problems, innovate, and create technologies that improve our lives. From understanding the air we breathe to designing the next generation of sustainable energy solutions, these fundamental principles of chemistry are at the very heart of scientific progress. So keep exploring, keep asking questions, and remember, science is everywhere and it's incredibly cool. Consider the world.